Hello students, welcome to Educate. Today we are going to continue with the numericals of chapter Ray Optics. In previous lecture we have done till question 9.4. Today we will start with question number 9.5 onwards. So let's see the question. Here, question says, a small bulb is placed at the bottom of a tank containing water to a depth of 80 centimeter. What is the area of the surface of water through which light from the bulb can emerge out? The refractive index of water is 1.33. Consider the bulb to be a point source. Here we are going to make use of the concept of total internal reflection. So let's consider the tank. Suppose this is the tank. Here there is bulb, light source. So we can draw perpendicular at this point. Suppose light ray is going like this. Similarly, in this direction, light ray will go like this. At this point, suppose this angle is I, and if it satisfies the condition of total internal reflection, it means this is critical angle. The same is true here. This is critical angle I. So the same will be true here. This is I. This is also I. So if light is incident at a critical angle, then it will pass like this. So no light will come out. But here, if ray goes like this, then light will come out. So this is the portion from where light will come out. So this circular portion is to be considered. So suppose this is R. So we have to find out the area of this circular portion, pi r square. And here this is height. The basic concept that we know is sin I is equal to 1 upon mu, where mu is a refractive index of the liquid. So in order to get sin I, what do we need? We need perpendicular upon hypotenuse. So we can write perpendicular is r, divided by hypotenuse will be a root of r square plus h square, right, equal to 1 upon mu. Here our concern is to find pi r square. So if we get r from here, we can easily calculate. So if we square it, so what do we get? R square equals 1 upon mu square times r square plus h square. Now we can take this term to LHS. R square minus r square divided by mu square equal to h square, right? Take r square common, then 1 minus 1 upon mu square is equal to h square, or r square will be equal to r square equal to h square divided by, either you write mu square minus 1, take LCM, and then take mu square in numerator. Up to here, is there any problem? Here what I have done, taken LCM, mu square minus 1 divided by mu square, and the same thing is written here, mu square minus 1 upon mu square, so mu square goes into numerator. Now what do we need? We need pi r square. So for this, we just multiply this result by pi. So we can say pi h square mu square divided by 1 minus mu square. So this will give our required result. Now we can put the values, so that let's denote it as A. So A will be equal to, this is 3.14 into height. Here height means depth is given as 80 centimeter. So just keep it in centimeter. So 80 square pi times h square times refractive index is given 1.33. 1.33 square whole divided by 1 minus 1.33 whole square. Is it correct? No. Here it is written by mistake. I have written here mu 1 minus mu square. It should have been mu square minus 1. So do one thing, put here minus sign and make it negative. So it will be same. Now we evaluate it. So just give 1 minute to evaluate it. So after evaluation, you will get 2600, and this will be in centimeters square. If you divide it 100 into 100, so what do you get? Two zeros, 2.6 meter square. 1 cm square 1 upon 100 into 1 upon 100 meter square. So that is why it is divided by 100 into 100. This result was in centimeter. So either you can write this radius and height in terms of meter also, you will get same result. I think you have understood. If you need a quick recap, I can give it to you. That is possible. So here so what you have observed in this question, the situation is very simple. As we have seen that here this is circle through which light comes out, and then here we have considered the case of critical angle. This angle is I, so this angle will be also I. So light will go like this. So this is the portion from where light comes out, and we have to find out this pi r square. This is R and this is H. So here sine theta can be found. So as I have done, sine I equal to perpendicular R upon hypotenuse will be this. So that will be equal to R square plus H square under root. And after that, you can proceed, and you know very well that sine I will be 1 upon mu. This is from concept of total internal reflection. So you can do it. This is very important question for your exam, and you can easily do. Now let's see next question. What does next question say? So here next question is, a prism is made of glass of unknown refractive index. A parallel beam of light is incident on face of the prism. The angle of minimum deviation is measured to be 40 degree. What is the refractive index of the material of the prism? The refracting angle of the prism is 60 degree. If the prism is placed in water of refractive index 1.33, predict the new angle of minimum deviation of parallel beam of light. So this is simple question, we can solve it. So what is formula for refractive index in case of prism? So A mu G is given by sine of A plus delta M, angle of minimum deviation, divided by 2 whole divided by sine A by 2, right? So just denote it as mu. sine of A. A means angle of prism, and that is given as 60 degree. And angle of minimum deviation measured to be 40 degree. It's given 40 whole divided by 2 divided by sine 60 degree divided by 2. Correct. Now you can evaluate. So this will come out to be 40 degree, 60 degree, 100 degrees. So this will become sine 50 degree divided by sine 30 degree. Now here we have to make use of the table. So from table we can write the value. So this comes out to be 0.766. 0.766 whole divided by this will become sine 30 degree 0.5. So this will give around 1.53. 1.53. So this is a refractive index of the prism. Now it is given that if prism is placed in water whose refractive index is 1.33, in that case what will be new angle of deviation? So everything will remain same except mu will become ratio, means the value that we have obtained 1.53 divided by the refractive index of water, that is 1.33, is equal to sine of A is 60 plus delta m divided by 2 divided by sine 60 by 2 degree. So we can further simplify 153 divided by 133 into, here sine 60 will become half, so we can multiply to this side, so half will come over here, and this will be sine of 60 plus delta m divided by 2. Right, we can simplify. So after simplification we will get delta m is equal to sine inverse and then 0.575. So calculation is simple. You can use calculator either or just calculate, and then thing is simple. So we have got the answer. Now consider next question. Now what is next question? Next question says a double convex lenses are to be manufactured from a glass of refractive index 1.55 with both faces of the same radius of curvature. What is the radius of curvature required if the focal length is to be 20 centimeter? Here we are going to make use of lens maker's formula. So 1 upon f equal to mu minus 1 upon r1 minus 1 upon r2. So this is formula, and now it is given that mu equal to 1.55 and both radii are same and focal length is also given 20. So we can write 1 upon 20 equal to 1.55 minus 1, and this will become 1 upon r, and this will become minus because we are considering these two faces. So 1 will be positive and this will be negative. So negative of that, r1 and r2, both r1 is r and sorry, r1 is r, r2 is minus r, right? So if we write, this will become 1 upon r. So we can say that it is 0.55 into 2 upon r. So our concern is to get r, so we can multiply this. So r will be equal to 20 times 0.55 times 2. So we can multiply, this will become 40 multiplied by 0.55 and then simplify to get r equal to 22 centimeter. I think this is very clear. Now let's see next question. Next question says a beam of light converges at a point P. Now a lens is placed in the path of the convergent beam 12 centimeter from P. At what point does the beam converge if the lens is a convex lens of focal length 20 centimeter and a concave lens of focal length 16 centimeter? So situation is simple. Here what is happening? Let's put a lens, but we will consider the situation when there is no lens. So we assume that these rays are converging at this point when there was no lens, but because of presence of lens, suppose point of conversion becomes this, right? So this was earlier position, this is new position when there is lens, right? Situation is given, a beam of light converges at a point P. So earlier these rays were focusing at this point, but because of presence of this lens, they focuses at this point. Now if the case is reversed, means if we take this as a concave lens, in that case these rays will converge somewhere here, so that we will discuss. But before that, let's try. So here beam 12 centimeter from P. Now a lens is placed in the path of the convergent beam 12 centimeter from P. So here this distance is given as 12 centimeter, right? So you have to find out what is the new position. So it is very obvious. We can assume that this is object whose image is formed over here, and focal length is given as 20 centimeter, which will be positive. So we can use lens formula. So what is lens formula? 1 upon V minus 1 upon U equal to 1 upon F. So we have to find out V. So 1 upon V is 1 upon F plus 1 upon U. 1 upon focal length. Focal length in this case is given as 20 centimeter and object distance is given as 12 centimeter. It will be positive, right? And now we can evaluate. So what will happen after evaluation? What do you get? Here we can write 60, then this will become 3, this will become 5. So V will be equal to 60 divided by 8. So 7.5 centimeter, right? So you can say that this length is 7.5 centimeter. So this is case when lens is convex. Now consider the case when lens is concave type. So as I told you, situation will get reversed. In place of this, suppose we imagine, or let's erase it. Now what is happening? These two rays are meeting here at point P. Now if we place a concave lens, now instead of Meeting at this point, these rays will diverge and they will meet somewhere here. This is I. So let's consider the information. This time focal length is 16 centimeter and this is concave. So f is given as minus 16 centimeter and we can apply the formula 1 upon f equal to 1 upon v minus 1 upon u, right? And object distance is same in both the cases. This is 12 centimeters, so u will be positive 12 because it is to the right of the lens. So we can write our concern is to get v, so 1 upon v is 1 upon u plus 1 upon f, right? And we can put the values 1 upon u is 12 and focal length of concave lens is minus 16. So what do we get? This will become 48 and then this is 4 and this is minus 3. That is 1 upon 48. So V will be 48 centimeter. So this length will be 48. I think you have understood. Now, let's take next question. Next question says, an object of size 3 centimeters placed 14 centimeter in front of a concave lens of focal length 21 centimeter. Describe the image produced by the lens. What happens if the object is moved further away from the lens? So, case is simple. We can consider here H1. Size of object is given as 3 centimeter and 14 centimeter in front of concave lens. So U is minus 14 cm and concave lens whose focal length is given as f equal to minus 21 cm, right? So we have to find out V. So V is to be found, H2 is to be found, M is to be found. Okay, using lens formula 1 upon V minus 1 upon U equal to 1 upon F. Let's put the values. So 1 upon V equals 1 upon F plus 1 upon U. So 1 upon F focal length is minus 21 and U is how much? U is given minus 14. Let's simplify. So this will become 42. So minus 3, sorry, minus 2 minus 3. So V is equal to 42 divided by minus 5, that is minus 8.4 cm. So this is value of V. Up to here there is no problem. Now we can find magnification. M equal to H2 upon H1 or V upon U. So here H2 is to be found. H1 is given as 3 is equal to V. We have got as minus 8.4 divided by U. U is given minus 14. So 84 divided by 140, right? So 6 divided by 10 or 0.6. So H2 will be equal to 0.6 into 3, which is 1.8 centimeter, right? and here this magnification is positive. What does this indicate? It indicates that image is virtual and erect, and its magnitude is less than 1, which means it is diminished. Correct? And describe the image produced by the lens. It's okay. Now, what happens if the object is moved further away from the lens? So here we can change the situation. We can take in place of 14, we can take minus 20, and then we can see what about V, whether the value of V increases or decreases. So we can calculate it to verify what is happening. So let's do it. So here, instead of this question, we were taking u14 earlier. Now let's change the value of u. Say, let's write it as minus 20 centimeter. F remaining same. F is 21 centimeter with a negative sign, and we have to see what is happening to V. So whether V is increasing or decreasing. In previous case, we have found V as 8.4. Now let's see. So 1 upon V equal to 1 upon F plus 1 upon U. We can put the values 1 upon F minus 21 and minus 1 upon 20. So what is LCM? It will be, suppose we write it as 420, 210, no, 420. Now, if we write 420, then 20, this will become 20 times. So minus 20, and this minus 21 times. So what about V? V is 420 divided by 41. So this time V is increasing. So V increases, right? So I think you have understood. So in this lecture, this is all. We will continue with the next question in next lecture. Thank you for watching. Team Educate.